Hello Stat 200, welcome to the full video lecture for Lesson 7, Normal Distributions. You were first introduced to the normal distribution in Lesson 2. The normal distribution is one specific type of symmetrical distribution, also known as a bell-shaped distribution. Over the last few lessons, you've approximated sampling distributions using bootstrapping and randomization methods. You may have noticed that many of the distributions that you constructed had similar shapes. These distributions are all approximately normal. This week, we're going to learn how we can use the normal distribution to approximate the sampling distribution when we're conducting a hypothesis test or constructing a confidence interval. These are the learning objectives that will be covered in this lesson. Let's get started by looking at the standard normal distribution. The standard normal distribution is a normal distribution with a mean of 0 and standard deviation of 1. You might see it described using this notation, where the n means that it's a normal distribution. The first number, here is 0, is the mean, and the last number, here a 1, is the standard deviation. The normal distribution is a continuous distribution. Theoretically, we can't compute the probability of any one specific z value. For example, we cannot determine the probability that z equals exactly 2, but we can find the probability for an interval of values. And that is essentially what the empirical rule does. Recall that according to the empirical rule, about 68% of a normal distribution falls within one standard deviation of a mean. About 95% falls within 2 standard deviations of the mean, and about 99.7% falls within 3 standard deviations of the mean. In the next learning objective, you're going to learn how to make all of these plots in Minitab Express. But first, there's one last point that I want to review before we move on, and that is z-scores. In Lesson 2, we learned that we can describe one observation in relation to the entire distribution in standard deviation units using a z-score. Here, we have the z-score formulas using sample statistic symbols on the left and using population parameter symbols on the right. In both cases, the z-score is the individual observation minus the mean divided by the standard deviation. This concept will come up again when we compute standardized test statistics later in this lesson, when we're exploring how the standard normal distribution can be used in hypothesis testing. This brings us to our second learning objective: determine the area under a normal distribution using Minitab Express. I'm going to take you over to Minitab Express to walk through how to create each of these standard normal distribution plots to find the area less than a z-score of 1, greater than a z-score of 1, between the z-scores of -1 and +1, more extreme than the z-scores of -1 and +1, and we'll work through this last plot, which is a normal distribution with a mean of 500 and standard deviation of 100. That's actually the scale that the SAT subscales are normed to, where we'll find the area greater than a score of 600. The process for making all of these plots is going to be very similar. I'm on a PC right now, but here's a screenshot from the Mac version of Minitab Express that shows where to find the probability distribution plot function. In the online notes, there are also instructions and silent videos for all of these procedures for both Windows and Mac versions of Minitab Express. Once you get into the dialog box, it should look identical on both versions. I'll take you over to Minitab Express now to walk through these examples. For the first example, I want to find the area on a z-distribution that is less than a z-score of 1. I'm on a PC, so I'll go to Statistics, Distribution Plot, Display Probability. The default in Minitab Express is to construct a z-distribution or standard normal distribution. This is a normal distribution with a mean of 0 and standard deviation of 1. I want to find the area less than a z-score of 1, That is what Minitab Express calls a specified x value. The area less than a value will be the area to the left of that value, and the x value is our z-score of 1. The area on a z-distribution that is less than 1 is 0.841345. Next, I'll show you how to find the area greater than a z-score of 1. Again, we'll construct a probability distribution plot to display a probability. We still have a specified x value of 1, but this time we want the area greater than 1, which is the area in the right tail. The area greater than a z-score of 1 is 0.158655. Now I'll show you how to find the area between two z-scores. We're going to find the area between z-scores of -1 and +1. Again, we'll construct our probability distribution plot to display a probability, and we're using the default standard normal distribution. Now we actually have two specified x values, and we want to find the area between them or in the middle. Our lower bound was -1, and our upper bound was +1. The area on a z-distribution between -1 and +1 is 0.682689. This should look familiar because according to the empirical rule, approximately 68% of a normal distribution will fall within one standard deviation of the mean. Our next example is to find the area more extreme than z-scores of -1 or +1. This time we're finding the area to the left of -1 and to the right of +1. We'll construct our probability distribution plot to display probability. We still have specified x values. This time we're trying to find the value in the tails. Because the z-distribution is symmetrical, you can enter +1 or -1 in here, and Minitab Express will mirror that for you. Note that what Minitab Express is giving us here is the area in each individual tail. So just like when we were doing two-tailed tests in StatKey, again, we'll have to add together the area in the left tail and the right tail to find the total area in the tails. The last example that I'm going to do is a little bit different. This time, we're going to have a normal distribution with a mean of 500 and standard deviation of 100 to find the area greater than a score of 600. We'll still construct a probability distribution plot to display the probability. Now we need to change the mean and standard deviation for our normal distribution to 500 and 100. We have a specified x value. We want to find the area greater than, or in the right tail, of a score of 600. On a normal distribution with a mean of 500 and standard deviation of 100, the area greater than a score of 600 is 0.158655. I'll take you back to the PowerPoint slides now, but we'll apply this later in this lesson. Our third learning objective is going to take us back to Minitab Express. This time, we want to determine the points that offset a given proportion of a normal distribution using Minitab Express. This is different from what we just did because now we'll have a proportion and we'll want to find the values on the x-axis that offset that area. I'm just going to walk through one example here, and that is how to find the z values that offset a given proportion of the z distribution. This is the procedure that you'll use when you're constructing a confidence interval and you're looking up the z multiplier. In this example, we're going to find the z-scores that separate the middle 99% of the z-distribution. If we were to draw this out, the proportion in the middle of the distribution would be 0.99, because Minitab Express is going to ask for proportions, not percentages. And the remaining 1%, or 0.01, will be split evenly between the two tails. Remember this, because what Minitab Express is going to ask for is the proportion split between the two tails, not the proportion in the middle. I'll take you to Minitab Express now to show you how to find those z-values. We're going to construct another probability distribution plot to display a probability. We want to find the z-values that separate the middle 99% from the outer 1%. We're still using the standard normal distribution. Now we're given a specified probability. We're going to select equal tails. Recall that if 99% is in the middle, then 1%, or 0.01, is split equally between the two tails. The z-scores that separate the middle 99% from the outer 1% are plus and minus 2.57583. When we go to construct a 99% confidence interval, these will be our z-multipliers. Our fourth learning objective is to summarize the central limit theorem. As we saw in the beginning of this video, many of the bootstrap and randomization sampling distributions that you have constructed in this course have been approximately normal. The central limit theorem states that if the sample size is sufficiently large, then the sampling distribution will be approximately normally distributed for many frequently tested statistics. This includes all of the statistics that we've worked with thus far in this course. In lessons 8 and 9, we'll learn what it means to be sufficiently large, but essentially it is determined by the point at which the sampling distribution becomes approximately normal. In practice, when we construct confidence intervals and conduct hypothesis tests, we often use the normal distribution as opposed to bootstrapping or randomization procedures in situations when the sampling distribution is approximately normal. This method is preferred by many researchers because z-scores are on a standard scale. They always have a mean of 0 and standard deviation of 1, and that makes interpreting the results more straightforward. They're also easier to compute. Essentially, what we'll be doing is transforming our bootstrapping or randomization distribution to a standard normal distribution. For example, for a hypothesis test, we'll convert our observed sample statistic to a z-score and then use that z-score to find the p-value on the z-distribution. We'll go through the steps of this procedure next. There are also a ton of examples in the online notes. Try to picture it as if you're taking the distributions that you made in StatKey and layering a standard normal distribution on top of it. Our fifth learning objective is to conduct a hypothesis test using a standardized test statistic. We'll use a 5-step hypothesis testing procedure. This is slightly different from the steps that you used in Lesson 5, because now in Step 2, we're computing the standardized test statistic, and in Step 3, we're using that test statistic to find the p-value on the z-distribution. I'll talk about each of these steps in a bit more detail now, and I'll walk through 2 examples. There are a lot of additional examples in the online notes. Step 1 is to check assumptions and write hypotheses. The assumption is that the sampling distribution is approximately normal. In Lessons 8 and 9, we'll learn about some conditions that can be met to satisfy this. For example, if the sample is at least a given size, or if there are at least a certain number of successes and failures. But for now, we're just going to look at the sampling distribution and decide whether or not it's approximately normal. The hypotheses are going to be the same as those that we learned in Lesson 5. Recall these tables that we had with all the possible combinations of hypotheses. If you need a review, This is towards the beginning of Lesson 5 in the online notes. Step 2, calculate the test statistic. This is the general form of a test statistic. This will work with all of the parameters that we've covered so far. So a single proportion, difference between two proportions, single mean, difference in two means, correlation, and simple linear regression slope. We can compare this formula to the formula for a z-score that we reviewed earlier. In both cases, we're drawing a standard normal distribution and mapping the value onto it. Recall that on a randomization distribution, the null parameter is the mean of the distribution, and the standard error is the standard deviation of that distribution. This formula for a test statistic converts the observed sample statistic to a z-score by finding how far from the hypothesized null parameter it is in standard error units. Step 3, determine the p-value. The test statistic that you compute in Step 2 is a z-value. We can map that z-value onto the z-distribution to find the p-value. The p-value will be the area under the z-distribution, more extreme than the test statistic, in the direction of the alternative hypothesis. For example, if we had a right-tailed test with a test statistic of z equals 2, the p-value would be the area to the right of a z-score of 2. If we had a left-tailed test with a z-score of -2, the p-value would be the area to the left of z equals -2. If this were a two-tailed test, the p-value would be represented in both tails, just like before. The z-distribution is symmetrical, so if the test statistic were -2, the p-value would be the area less than -2 and greater than +2. We would have to add these two tails together to find the p-value. Step 4, make a decision. We'll be using the same rules that we learned in Lesson 5. If the p-value is less than or equal to the alpha level, which in most cases is 0.05, we reject the null hypothesis. If the p-value is greater than the alpha level, we fail to reject the null hypothesis. And Step 5, state a real-world conclusion. This is where we go back to the original research question and state whether or not we have evidence of the hypothesized difference. Again, this is using the same rules that we learned in Lesson 5. If you rejected the null hypothesis, then the results are statistically significant and there is evidence of a difference in the population. You would go back to the research question or hypotheses to determine if that difference is right-tailed, left-tailed, or two-tailed. In other words, if there's evidence that the parameter is greater than a given value, less than a given value, or different from a given value. If you fail to reject the null hypothesis, the results are not statistically significant and there is not evidence of a difference in the population. Let's work through some examples. Here's our research question. Are more than 60% of all World Campus Stat 200 students adult learners? In a random sample of 100 students, 66 were adult learners. StatQ is used to construct a randomization distribution, which we are given here. In Lessons 8 and 9, we'll learn how we can use formulas to construct the sampling distribution, but for this week, we'll still be working with the randomization distributions from StatQ. Let's work through the 5-step hypothesis testing procedure. Step 1, check assumptions and write hypotheses. The assumption is that the sampling distribution is approximately normal. The distribution is approximately normal, so this assumption has been met. That means that we can approximate the sampling distribution using the standard normal distribution. Essentially, what we'll be doing is translating this sampling distribution from StatQ into the standard normal distribution. Now we can write our hypotheses. Our null hypothesis is that the population proportion equals 0.60, Our alternative hypothesis is that the population proportion is greater than 0.60. In step 2, compute the test statistic. This is the general form of a test statistic. This translates the observed sample statistic to a z-score. The sample statistic is the proportion in the original sample. 66 divided by 100 gives us a sample statistic, in this case a sample proportion, of 0.66. The null parameter is the value from the hypotheses, that is 0.60, and the standard error we'll get from the stat key sampling distribution, that value was 0.049. We plug these values into our formula, and we get a test statistic of 1.224. Step 3, determine the p-value. The p-value is the area under the z-distribution that is more extreme than the test statistic in the direction of the alternative hypothesis. The test statistic was 1.224. When the z-distribution is superimposed on top of the randomization distribution, z equals 1.224 falls on top of p hat equals 0.66. That's because our test statistic is just converting that observed sample statistic to a z-score. Our alternative hypothesis was that p is greater than 0.60, so this is a right-tailed test. Our p-value will be the area to the right of our test statistic of z equals 1.224. I'll take you over to Minitab Express now to show you how we can find that proportion. We'll find our p-value by constructing another probability distribution plot to display the probability. We have a standardized test statistic. Because it's standardized, we're going to be mapping it on to the standard normal distribution, or z-distribution. That's a normal distribution with a mean of 0 and standard deviation of 1. Our test statistic is a specified x value. Recall our alternative hypothesis was that p is greater than 0.60. This is a right-tailed test. Our x value is our standardized test statistic of 1.224. Our p-value is the area on the standard normal distribution that is greater than our test statistic in the direction of the alternative hypothesis. Here, our p-value is 0.110476. Here, on the left, is the randomization distribution from StatKey, and on the right is the normal distribution that we just made in Minitab Express. Note that the p-values are very similar. They won't be exactly the same because there are gaps in the randomization distribution and it's not exactly normally distributed. But if the sampling distribution is approximately normal, the p-values will be similar using the two methods. When we put the z-distribution on top of the randomization distribution, again, we can see that the area that we're covering with the p-value is very similar. If you're reading research articles, you're more likely to see this method using the z-distribution as opposed to randomization methods. Part of this is because historically the z method has been easier to calculate. It can be done with little or no technology, whereas the randomization methods require some computing power. Today, we have applications such as StatKey and Minitab Express that will run these simulations relatively quickly for us, but in the past, these options weren't available to researchers. Another perk of using the z-distribution method is that it puts the test statistic on a standardized scale. If you say z equals 1.224, every statistician knows that this means that you're 1.224 standard deviations or standard errors above the mean. So that's why we cover both approaches in this course. In all of the remaining lessons, the emphasis will be on the standardized methods, so the new method that we're introducing in this lesson. Going back to our example, we found our p-value by constructing a z-distribution in Minitab Express. Step 4, we make a decision. Our p-value is greater than the standard 0.05 alpha level, so we fail to reject the null hypothesis. This means that our results are not statistically significant. And step 5, state a real-world conclusion. There is not evidence that more than 60% of all World Campus Stat 200 students are adult learners. Let's walk through one more quick example. Our research question is, do the mean arrival times differ for Delta and United flights? What we're going to be looking at is how early or late each flight is. An arrival time of 0 would mean that the flight is right on time. A negative arrival time would mean that they're early, and a positive arrival time would mean that they're late. This is a data set that is built into StatKey if you go to construct a randomization distribution for the difference in two means. Here we have the original sample, where we can see that on average, United flights are 9.756 minutes late, and Delta flights are 2.623 minutes early. The difference between the two sample means is negative 12.38. While the samples are skewed to the right, the sample sizes are very large, so according to the central limit theorem, we should expect the sampling distribution to be fairly normally distributed. We have the sampling distribution that was made in StatKey. The method that I used to make this sampling distribution is exactly what we did in Lesson 5, so I'm not going to walk through that here. Let's use the 5-step hypothesis testing procedure to address this research question. Step 1, check assumptions and write hypotheses. The assumption is that the sampling distribution is approximately normal. With the large sample sizes, the sampling distribution is approximately normal. That assumption is met, so we can use the z-distribution to approximate the sampling distribution here. Next, we write our hypotheses. We want to know whether or not there is a difference between the two population means. The null hypothesis is that mu sub 1 minus mu sub 2 equals 0. In other words, there is not a difference between the two population means. Our alternative hypothesis is that mu sub 1 minus mu sub 2 does not equal 0. In other words, there is some difference. This is a two-tailed test. Step 2, compute the test statistic. Here's the general form of a test statistic. The sample statistic is the difference in the original sample. That was x bar 1 minus x bar 2, and it equaled negative 12.38. The null parameter is the value from the hypotheses. That was 0. And the standard error comes from the sampling distribution. That value was 1.751. We plug these values into our formula, and we get a standardized test statistic of negative 7.070. Step 3, determine the p-value. I'll take you to Minitab Express to construct a z-distribution. This is a two-tailed test, so the p-value will be the area less than a z-score of negative 7.070 and greater than positive 7.070. I'll construct another probability distribution plot to display a probability. We have a standardized test statistic, so we are working on a z-distribution. Our test statistic is a specified x value. This is a two-tailed test, so the p-value will be equally split between the left and right tails. Our z-test statistic was negative 7.070. We can see here the area in both tails is very small, Theoretically, the p-value can never equal 0, so what I would say in this case is that p is less than 0.0001. Step 4, make a decision. With the p-value being less than the standard 0.05 alpha level, we reject the null hypothesis. The results are statistically significant. In step 5, state a real-world conclusion. There is evidence that the mean arrival times in the population differ for Delta and United flights. If you would like to see more examples, there are quite a few in the online notes. There are also some towards the end of section 5.1 in the textbook. Our last learning objective is to construct a confidence interval using the standard form. This is the standard form of a confidence interval, the sample statistic plus and minus the z multiplier times the standard error. This should look very similar to the formula that we used in lesson 4 when we were constructing a 95% confidence interval using the standard error method. Then we used a multiplier of 2 because we were constructing a 95% confidence interval, and according to the empirical rule, or 95% rule, approximately 95% of a normal distribution will fall within 2 standard deviations of the mean. This week, we'll learn how we can construct confidence intervals with any level of confidence. We can use Minitab Express to construct standard normal distributions to find the z multipliers for any confidence level. Let's walk through a couple of examples. In a random sample of 100 World Campus Stat 200 students, 66 were adult learners. Construct a 90% confidence interval to estimate the proportion of all World Campus Stat 200 students who are adult learners. StatKey was used to construct a bootstrap sampling distribution. This distribution is approximately normal, so we can use the general form of a confidence interval here. The sample statistic is the proportion in the original sample. P hat equals 66 over 100. This gives us a sample statistic of 0.66. The z multiplier we're going to find by constructing a z distribution in Minitab Express to find the z values that separate the middle 90% of the z distribution from the outer 10%. Again, we'll construct a probability distribution plot to display a probability. We're constructing a z distribution, which is a normal distribution, mean of 0, standard deviation of 1. We have a specified probability. We're constructing a 90% confidence interval, so we need to find the z-scores that separate the middle 90% from the outer 10%. And that 10% will be split equally between the left and right tails. Our z multiplier is 1.6445. The standard error we can get from our StatKey bootstrap distribution. That value was 0.048. We plug these values into our formula and we get a 90% confidence interval of 0.581 to 0.739. I am 90% confident that in the population of all World Campus Stat 200 students, between 58.1% and 73.9% are adult learners. I'll do one more example. Here we're going to construct a 99% confidence interval to estimate the difference in mean commute distances in Atlanta and St. Louis. This is a data set that is built into StatKey when you go to construct a bootstrap distribution for the difference in two means. On the original sample, we can see that the mean commute distance in St. Louis was 14.156 miles, and the mean distance in Atlanta was 18.156 miles. The difference in these sample means was 4 miles, with Atlanta having the larger commute distance. We also have the sampling distribution that was made in StatKey. This sampling distribution is approximately normal, so we can use the standard normal distribution method to construct this confidence interval. Here's the general form of a confidence interval. The sample statistic is the mean difference in the original sample. That was 4. The z multiplier we're going to find by constructing a z-distribution in Minitab Express to find the z values that separate the middle 99% of the distribution from the outermost 1%. Again, we'll construct a probability distribution plot to display a probability. We have equal tails with 99% in the middle, 1% or 0.01 is split equally between the tails. Our z multiplier is 2.57583. The standard error we can get from the sampling distribution that was made in StatKey. That value is 0.775. We plug these values into the formula, and we get a 99% confidence interval of 2.004 to 5.996. I am 99% confident that in the population, the difference in the mean commute distances in Atlanta and St. Louis is between 2.004 miles and 5.996 miles. This concludes the Lesson 7 lecture video. If you're looking for additional examples, there are quite a few in the online notes in this lesson. You're also encouraged to post any questions that you have to the Lesson 7 discussion board in Canvas.